Today, we are going to explore the concept of virtual memory, a crucial aspect of modern operating systems. Virtual memory provides the separation of logical and physical address spaces, which is essential for efficient and secure computing. Virtual memory is a memory management technique that provides an idealized abstraction of the storage resources available to a program. It creates the illusion of a very large main memory, which separates logical memory from physical memory and allows efficient and safe memory sharing between different processes. Here, we differentiate between the logical and physical address spaces. The logical address space is generated by the central processing unit, or CPU, during the execution of a program. Physical address space refers to the actual random access memory, or RAM locations. Logical addresses are translated to physical addresses before accessing memory. This translation is a fundamental aspect of virtual memory management. The Memory Management Unit, or MMU, plays a crucial role in address translation. The MMU translates logical addresses to physical addresses using mapping tables. This translation is transparent to the running program, which means the program does not need to be aware of the actual physical address. Programs can use a contiguous address space, regardless of physical memory allocation. This mechanism provides memory protection between processes and enables efficient memory utilization through sharing and swapping. Paging is a key concept in virtual memory. Virtual memory is divided into fixed-size units called pages. Physical memory is divided into same-sized units called frames. The page table maintains mappings between virtual pages and physical frames. Pages can be mapped to frames in any order, providing flexibility in memory allocation. Not all pages need to be in physical memory at once. Some can be stored on disk. Here's how virtual address translation works. A virtual address is divided into two parts: the page number and the page offset. Similarly, a physical address is divided into the frame number and frame offset. The virtual address is 2 raised to the power of p plus bytes. Page size is 2 raised to the power d bytes. The physical address is calculated by multiplying the frame number by the page size and adding the offset. Physical memory equals 2 raised to the power of f plus bytes. Consider an example: if the CPU generates a virtual address 0x3A92, then the page number is 0x3A, which is 58, and the offset is 0x92, which is 146. The memory management unit looks up the page table and finds that page 58 is mapped to frame 14, which is 0x0E. The physical address is then calculated as 14 times 256 plus 146, which equals 3,584 plus 146, resulting in 0x0E92. Let's look at the structure of a page table. A typical page table entry consists of several fields. The frame number indicates the physical frame location in memory. The present bit indicates if the page is in physical memory. The modified bit indicates if the page has been modified. The reference bit indicates if the page has been accessed. The valid bit indicates if the mapping is valid. Page tables enable efficient memory management through status tracking, support page replacement algorithms with usage information, provide protection through access control bits, and allow the operating system to detect and handle page faults. Now we'll describe the process of page fault handling. First, the memory management unit detects that a requested page is not in physical memory because the present bit is 0. The central processing unit then generates a page fault exception and transfers control to the operating system. The operating system locates the page on disk and loads it into an available physical frame. Finally, the operating system updates the page table, sets the present bit to 1, and restarts the instruction. There are numerous performance benefits of virtual memory, including allowing programs to execute even when only partially loaded in memory, reducing input-output operations by keeping frequently accessed pages in memory, enabling memory caching for faster access to frequently used data, and supporting demand paging to load only needed pages. Additionally, virtual memory provides memory isolation between processes, enables memory protection through access control bits, allows efficient memory sharing for libraries and shared memory, and simplifies memory allocation and program loading. Without virtual memory, processes compete directly for physical memory, leading to fragmentation and inefficient utilization. With virtual memory, only active parts of processes reside in physical memory, and shared libraries can be efficiently utilized. Disk storage acts as swap space for inactive pages. In summary, virtual memory creates a separation between logical and physical address spaces through dynamic address translation. Paging provides a flexible way to manage memory allocation and enable efficient memory utilization. Virtual memory provides process isolation, memory protection, and allows programs to run with limited physical memory. In our next videos, we will explore related topics such as page replacement algorithms, thrashing and working sets, multilevel page tables, translation look-aside buffers, segmentation with paging, and memory-mapped files. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.